In this video, we look at the work on momentum and impulse required by Unit 3 of the new WJEC Further Mathematics specification. We need to be able to understand and use both momentum and impulse, together with the conservation of momentum. In addition, we need to be able to use Newton's experimental law to deal with the impact of two bodies moving in the same straight line, or the impact of a body moving at right angles to a plane, which is likely to be the direct impact of an object with something like a wall. The momentum of a body is given by mv, where v is the velocity of the body, and this means that momentum is a vector quantity, and the units of momentum can be written as kilogram meters per second. The impulse of a force acting for time t is F times t. Again, this means that the impulse is a vector quantity, and the units of impulse can be written as Newton seconds. One of the consequences of Newton's laws of motions is that the impulse acting on a body gives us the change in momentum of that body, and the change of momentum is the final momentum minus the initial momentum. Conservation of momentum states that if we've got two particles interacting in such a way that no external impulses act, then the total momentum of the system immediately before the interaction equals the total momentum of the system immediately after the interaction. And this is particularly useful when we're dealing with the collision between two objects. When dealing with conservation of momentum questions, it's a really good idea to be clear before and after diagrams, and also to make it really clear when applying the conservation of momentum which direction you are regarding as being your positive direction. And Newton's experimental law of restitution says that if we have two bodies in a collision, the ratio of the speed of separation of the bodies to the speed of approach is constant, and just depends on the material on which those two bodies are made. And that constant is called the coefficient of restitution of the two bodies. We often will use the letter E when we want a letter for the coefficient of restitution, but note that this letter E in mechanics is completely different from the 2.718 that you probably have met by now in your pure maths. So we've got E is the speed of separation divided by the speed of approach. If E is equal to 1, then the collision is said to be elastic or perfectly elastic, and the kinetic energy is conserved in the collision. On the other hand, if E is less than 1, then the collision is said to be inelastic, and kinetic energy will have been lost in the course of the collision. So we'll now move on and have a look at some examples of momentum questions. So in the first example, we have a shell exploding into two parts, and we're told that the larger part has a mass of 540 kilograms and a speed of 18 meters per second immediately after the collision. We have to find the speed of the smaller part and describe the direction in which it's moving, and we have to calculate the kinetic energy created by the explosion. So we'll start by drawing some diagrams. So before we have the shell, we have the explosion, and then we have the shell splitting into two parts, one of which is of size 540 kilograms, moving at a speed of 18 meters per second. Now our first assumption is going to be that there's been no loss of mass of the shell in the course of the explosion, so that the second part of the shell will have a mass of 60 kilograms. Now, during the course of the explosion, just before the explosion occurred, there was no momentum. So that means the final momentum must be equal to 0 because there are no external impulses acting on the system. So the velocity of the small part the momentum of the small part must be equal and opposite to the momentum of the large part, which means that the velocity of the small part must be in the opposite direction to the velocity of the large part. So we can put that onto our diagram. So we've now got our completed diagram. We can now apply the conservation of momentum to the setup. So applying to the conservation of momentum, and we'll make it clear that we're regarding to the right as being our positive direction. Then the momentum before must equal the momentum after. The momentum before is 0. The momentum after is 540 times 18. That's the momentum of the larger part. Whereas the momentum of the smaller part is 60 times minus v. Now remember that the momentum is a vector quantity, so that our velocity of the smaller part has to be minus v. So we're regarding to the right as being the positive direction. So we've got 60v must equal 9,720, which gives me v is 162 meters per second. So the speed of the smaller part is 162 meters per second in the opposite direction to the motion of the larger part. The kinetic energy created by the explosion is going to be the kinetic energy of the large part plus the kinetic energy of the small part. We need to remember that kinetic energy is a half mv squared. So the kinetic energy of the larger part is half times 540 times 18 squared, and the kinetic energy of the smaller part is a half times 60 times 162 squared. So the kinetic energy gained is 874,800 joules. This is going to be an underestimate of the total energy created by the explosion, because in the course of an explosion we're certainly going to get some sound energy, we're certainly going to get some light energy, and we may well also get some heat energy created. So we'll now move on to a second example. We have a particle of mass 2 kilograms moving speed 12 meters per second on a smooth horizontal surface. When it collides directly with a particle B of mass 3 kilograms moving speed 7 meters per second in the same direction as A. We're told the coefficient of restitution between the particles is 0.6. We've got to find the speed of A and B after the collision, and we have to find the magnitude of the impulse exerted by A on B during the collision. So we're going to start by drawing our before and after diagrams for the collision. So before the collision, we have A moving at 12 meters per second, and we have B moving at 7 meters per second. And after the collision, in the diagram, we have shown B moving at V meters per second to the right, and A moving at U meters per second to the right. Now, one of the nice things is, if we have got the direction of motion of A incorrect, and that A rebounds in the opposite direction after the collision, then that will come out from the algebra. As long as we make the diagrams clear, the algebra will do the work for us thereafter. Why have I chosen to put the arrows on in that way? Well, looking at the initial diagram, all of the momentum is to the right, so the net momentum has certainly got to be to the right in the after diagram. And the way I've put the arrows here is one of the two possible ways of achieving that. So, we have the conservation of momentum. We'll certainly take the positive direction as being to the right. The initial momentum is 2 times 12 plus 7 times 3. The final momentum is 2 times u plus 3 times v. And if we tidy that equation up slightly, we get 45 must be 2u plus 3v. We've then got the restitution equation. So the restitution equation tells us that 0.6 is the ratio of the separation speed to the approach speed. Now, the separation speed is the speed at which B is moving away from A, which, if we look at our after diagram, is V minus U. Whereas the approach speed is the speed at which A is catching up with B before the collision, which is at a speed of 5 meters per second. And tidying that equation up, we've now got that 3 must be V minus U. So we've now got a pair of simultaneous equations, which we can solve, probably using our calculator, to obtain U equals 7.2 and V equals 10.2. So the speed of A after the collision is 7.2 meters per second, and the speed of V after the collision is 10.2 meters per second. The fact that both of these are positive means that I have got the directions of the final speeds correct in my initial diagrams. Finally, on this question, we have to find the magnitude of the impulse exerted by A on B during the collision. So we're going to just consider B alone. Before the collision, it's moving at 7 meters per second to the right. It then receives an impulse from A during the impact, and after that impact, it's moving at 10.2 meters per second to the right. So applying impulse equals change in momentum on B, we've got the impulse I must equal the final momentum of B, which is 3 times 10.2, minus the initial momentum of B, which is 3 times 7, which gives me that the impulse must be 9.6 Newton seconds. And we'll now move on to our final example, which is a slightly amended exam example. We have a particle P of mass 2 kilograms is moving with speed u meters per second in a straight line on a smooth horizontal surface. Particle P collides directly with another particle Q of mass 5 kilograms, which is at rest on the surface. Immediately after the collision, P moves with 2 meters per second in a direction opposite to its original direction of motion, and the speed of Q is 3 meters per second. So we have to find the value of U and determine the coefficient of restitution between P and Q, and calculate the magnitude of the impulse exerted by P on Q. And those three questions form the first 3/5 of the question. So, we're dealing with a collision question. We need a clear before and after diagram. So before the diagram, we have P moving at u meters per second and Q stationary. After the collision, we have P moving in an opposite direction to its original motion at 2 meters per second, and Q moving off at 3 meters per second. Q must be moving off to the right because before the collision the net momentum is off to the right. Therefore the net momentum, the total momentum after the collision, must be to the right. P is giving us momentum to the left, in other words a negative momentum, so Q must have positive momentum. It must be going off to the right. Okay, so we can now apply the conservation of momentum, and we'll take to the right as being our positive direction. The initial momentum is simply 2 times u plus 5 times 0. The final momentum is 2 times minus 2 for P plus 5 times 3 for Q. So we have 2u must equal 11, so the initial speed of P must be 5.5 meters per second. It's now relatively easy to calculate the coefficient of restitution between P and Q. So we know the coefficient of restitution is the ratio of the separation speed of the two particles to the approach speed of the two particles. Just after the collision, the particles are moving away from each other at a speed of 5 meters per second, whereas just before the collision, P is approaching Q at a speed of 5.5 meters per second. Q is stationary, so the approach speed of P to Q is 5.5 meters per second. So we've got E is 5 divided by 5.5, or 10/11. To calculate the magnitude of the impulse exerted by P on Q, we need to consider Q carefully during the course of the impact. Just before the collision, it's stationary. During the collision, it receives an impact from P, and just after the collision, it's moving off at 3 meters per second. So applying impulse equals change in momentum, the final momentum of Q is 5 times 3. The initial momentum of Q is 0. So we've got I is 5 times 3 minus 5 times 0, which gives me I equals 15 Newton seconds. Now the next part of the question tells us that after the collision of P and Q, Q strikes a vertical wall which is perpendicular to its direction of motion. We're told the coefficient of restitution between Q and the wall is 0.25, and we have to calculate the speed with which Q rebounds from the wall. Okay, so we need a new diagram. So we're considering the motion of Q and the wall. So we know that Q is moving at 3 meters per second as it approaches the wall. It then receives an impact from the wall, so that's an impulse from the wall as it hits the wall, and then it rebounds with speed v. The restitution equation says that the coefficient of restitution between Q and the wall, which is 0.25, will be the separation speed divided by the approach speed. The separation speed is v, the approach speed is 3, so we've got v over 3 must equal 0.25, so v must be 0.75 meters per second. So Q rebounds from the wall at 0.75 meters per second. Applying impulse equals change in momentum. This time we'll apply it to the left because the impulse J is acting to the left. We've got the impulse equals the final momentum of Q to the left minus the initial momentum of Q to the left. The final momentum of Q to the left is 5 times 0.75. The initial momentum of Q to the left is 5 times minus 3. Now the minus 3 there is important. It's minus 3 there because we are applying impulse equals change of momentum to the left. So to the left is our positive direction. So that initial velocity of Q there, which is 3 meters per second to the right, must be recorded as a velocity of minus 3 if we are regarding to the left as being our positive direction. And that gives me J equals 18.75 Newton seconds.